we are starting out today with some Tyler DeWitt. Okay, so we are going to page 25. What page are we going to? 25.
Okay, let's keep learning about ionic bonding. First thing I want to talk about is why electrons move from sodium to chlorine and not from chlorine to sodium. Okay, so in the first step of ionic bonding, this one electron from sodium moves over here to chlorine to fill this one space. But people often ask, why couldn't these 7 electrons from chlorine move over and fill these 7 empty spots in sodium? Well, that's a great question. The answer has to do with a topic called electronegativity. Okay? Electronegativity is a measure of how badly an atom wants electrons. The higher an atom's electronegativity, the more greedy it is for electrons, the more it wants to try to steal them from other atoms. So in ionic bonding, there are electron givers and there are electron takers. This has to do with whether an atom is a metal or a nonmetal. Okay, so nonmetals, like chlorine, all have a very high electronegativity. Okay, they are very greedy. They want other electrons very, very badly. On the other hand, metals, like sodium, have a low electronegativity. Okay, they're not so greedy for electrons and they're willing to give them up. So that's why electrons move from sodium to chlorine and not the other way around. They move from the atom with low electronegativity, low greediness, to the atom with high electronegativity. And this is the way it always works in ionic bonding. The metals, like sodium, are the electron givers, and the nonmetals, like chlorine, are the electron takers. Electrons always move from the metal to the nonmetal. And in ionic bonding, because of that, the metals always become positively charged because they lose electrons, and the nonmetals always become negatively charged because they gain electrons. It's all about electronegativity, the greediness of an atom for electrons. Now I want to talk a little bit about the shape and structure that ionic compounds make. Okay, so we've got sodium here, we got chlorine here. And we've talked about how they get opposite charges and they end up sticking together, forming a shape kind of like this. Okay, but so far, we've only talked about two atoms, one of each. In nature, rarely would we find just two atoms, okay? Usually, there are going to be a lot more than two atoms that want to exchange electrons and combine together. So what happens when we have a bunch of atoms that could all do ionic bonding? Okay, well, what you might want to think of is each pair of these atoms could form a structure kind of like this, okay? But here's the thing. These guys wouldn't stay separate. Okay, this is super important. They wouldn't stay separate because opposite charges attract not only in groups of two. Okay, so this positive and this negative, they're attracted to each other, but this positively charged sodium will also be attracted to this negatively charged chloride over here. Okay, so these two things are going to end up connecting to each other because of that attraction, right? And then there's this guy over here, and this positively charged sodium could be attracted to this negatively charged chloride, and this negative charge could be attracted to this positive charge. So this will come together just like here, okay? And so we start building a much bigger shape. If we get a bunch of these sodium and chlorine atoms getting charges and coming together, we're going to end up with a shape like this. This is called a lattice structure, okay? Up with a shape like this. This is called a lattice structure, okay? And you can see how these ions are packed really closely together and how they're making this larger shape. Okay, here we have a negative ion and it's surrounded by 4 positive ions because they're all attracted together. Okay, and over here we've got a positive ion that's surrounded by a whole bunch of negatively charged ions. And just Just in general, through the lattice structure, we alternate plus, minus, plus, minus, plus, minus, because all of these opposite charges are attracting together to make this lattice structure. So the important thing to keep in mind is that ionic bonding, when you're talking about more than just two atoms, it doesn't only make these small groups of two, but these groups are going to be attracted to each other, and they are going to make much bigger structures that are going to become these lattice structures. So that's super important when you're thinking about the structure of ionic compounds. Now, as we go forward, we'll probably continue focusing on just two atoms at a time. But whenever you see a shape like this, keep in mind that it's just one part of a bigger lattice structure that you get when a whole bunch of these different units come together. Okay, finally, let's just talk naming really quickly. Okay, so when this ionic bond forms, we start with sodium, Na, and chlorine, Cl. Okay, sodium loses one of its electrons to chlorine, so that gives us a sodium ion, which we can abbreviate as Na+. And since chlorine gets an extra electron, it becomes a chloride ion, Cl-. Okay, now we call it chloride because chloride is the negative version of chlorine. It becomes a negative ion and it becomes chloride. Sodium, on the other hand, we call it sodium whether it's neutral or whether it's positively charged. So we have a positively charged sodium, negatively charged chloride, and they stick together. So now they make a compound because these two things have connected, okay? And the compound, we call that sodium chloride, and we write its chemical formula as NaCl. Now, here's one common mistake that people make that I don't want you to make, okay? They're writing the formula for sodium chloride and they see that this has a positive charge and this has a negative charge. So often they'll write it as Na+, Cl-. Now that's not right. Don't do it, okay? It's true that sodium does have a positive charge and chlorine has a negative charge here. But when the two of them come together, the positive and the negative charge, they cancel out. So it's like the whole thing combined doesn't really have any charge anymore. So that's why we don't put the plus and the minus when we're writing the chemical formula. It's just NaCl. We leave out the plus and we leave out the minus. Okay? One other thing that sometimes happens is when people are asked to name this compound, okay, so like the name sodium chloride, they try to keep these charges in. So they call it sodium plus chloride minus. And again, you don't want to do that because we don't keep the charges. So don't call it sodium plus chloride minus. It's just sodium chloride, NaCl, even though these atoms still have a charge. Because they're like balancing each other out in this compound, we don't worry about the charge when we're naming it.
In this video, we're going to go over how to
I think. Or is it 29? No, it's page 29. You're going to do these questions. Now, there is an error on page 29, and that is in question 3. The first A says metals, B should not also say metals, it should say non-metals, because otherwise you have two questions that are the same. So take a few minutes to do that. While you're doing that, I'm going to hand back the test to people who wrote on Friday or whenever the heck it was I saw you Thursday. We'll just, right in there is good. Thank you. And if you're having troubles finding the answers, especially to say number 4C, look back on page 27. Okay, you'll find the answers there. Who needs more time on this? A few minutes more? Okay. Let's give it another maybe 2 minutes. I'd like you to wrap up, okay? Okay, my friends. We are just about ready here. Let's go over this because it won't take very much time at all. Are metals electron givers or electron takers? Givers. Are non-metals electron givers or takers? Takers. What does the term electronegativity mean? Yes? A measure of, I'm just going to say how much an atom wants an electron. Okay, basically it's how strongly do they pull it. Yeah. Do metals have a high electronegativity or do they have a low electronegativity? They have a low electronegativity. Non-metals, high or low? High. A single unit of an ionic compound, and this is what you had to find on page, actually this one was also on page 27. A single unit of an ionic compound is called a formula unit. What shape should I be drawing, or shapes, if I am drawing a formula unit? One big circle, one small circle. That's like the worst circle ever. It looks like an egg or something, but that's okay. In general, the positive ions are the small ones, and the negative ions are the big ones. No one's curious as to why? Yes, why? Why? So if you have a sodium atom, and in its outer shell, there is an electron, right? If it gives away that electron, that outer shell is now empty, and so the next shell in is the size of the atom. So the atom has gotten smaller. It's gone from having this many shells to having that many shells. Yeah, that many filled shells, right, with electrons in them. So it actually gets smaller. Whereas if you put an electron in, like you do with a nonmetal, you actually get a little bit of extra repulsion between those negative electrons, and it makes it a little bit bigger. Okay? What do we call this attractive force between the positive and negative ion? Actually, my arrowhead should be on the other side. That is an ionic bond, yes. The attractive force between a positive ion and a negative ion is an ionic bond. In reality, many of these single units, like we just drew, what do we call those single units? Formula units. Bond together in a large three-dimensional array called a lattice structure. Lattice structure, which is also known as a crystal lattice. Okay, very, very good. All right. We are going to go now, if I can get there, to 3.2D and take a look at some names and formulas of simple ionic compounds. Much of this is going to be things that you've already maybe heard once or twice before. Maybe you remember it, maybe you don't. Okay, we're going to formalize things a little bit more. When we have a formula or a name of an ionic compound, and remember, an ionic compound is going to be a metal plus a non-metal. Who comes first in the name or the formula, the metal or the non-metal? It's always the metal that comes first. The non-metal comes second. Just like on the periodic table, if you look on the left side of the periodic table, those are all your metals, and on the right side are the non-metals. So the same thing in the formula. The left one is the metal, the right one is the non-metal. And in order to name it, it is super, super simple. Name the metal. So you might have, for example, calcium, sodium, iron, okay? You name the metal, don't do anything with the name, leave it alone, just read it off the periodic table. What do we do to the name of the non-metal? We change the ending to ide, I-D-E. So instead of chlorine, we would have chloride. Instead of oxygen, we would have oxide, etc. Okay? So if we're making a compound between magnesium and oxygen, what is its name? Well, we simply name magnesium. Oh, look. And then oxygen becomes, because it is the non-metal, so its name becomes oxide. Now, don't get fooled by the next one. If I say a compound forms between nitrogen and aluminum, don't get fooled into calling it nitrogen aluminide, okay? Who is the metal? Aluminum is the metal, nitrogen is the non-metal. You have to make sure that the aluminum goes first, aluminum, and then the non-metal goes second, and it's the one whose name changes to ide, nitride. Not nitrogide. Do you remember something about the names of anions? How many syllables do anions' names usually have? Usually 2. There's like one exception to that. I think it's selenide, but you won't come across that very often. So we can just say that they have 2 syllables. Does the word subscript ring any bells? Subscript, below writing. What kind of thing are we writing below the writing? We're writing a little number. Okay, so they are small numbers, and they are written at the bottom of an element symbol, and it tells us how many of that atom. But if there's only one, do we write a number? No. So sodium chloride, which is a 1-to-1 ratio, we don't write Na1Cl1, we just write NaCl. So here is sodium phosphide. So here we have sodium phosphide, and you can see how many sodiums do we have in that structure? We got 3. 1, 2, 3, which is why down below the sodium, what do we see? A little subscript 3. How many phosphoruses do we see? 1. And you'll notice no number means 1. Okay? If we have 3 Na pluses, the total negative charge, or sorry, positive charge, is how much? 3, right? We got 3 positive things, so we have a total positive charge of 3 plus. If we have 1 P, which has a 3 minus charge, the total negative charge is how much? Tell your partner, what's our total negative charge? We have 1 P3 minus. So what is our total negative charge? This is not rocket science. Like it is easier than you think. We have 1 3 minus, so the charge is 3 minus. Okay, excellent. Okay. What is the total net charge? Yeah, the net charge is equal to 0. And in fact, this is really important. All compounds have a net charge of 0. They are always neutral, okay? Because what will happen is if there's another ion, if it's not neutral, it will go zooming around the universe until it finds, like, well, not really zooming around the universe, but it will grab anything with a positive charge if it happens to be negative, or vice versa, until it's all neutral. What do we call this entire structure? It's an ionic compound. Because it's made of a metal and a non-metal. Sodium is a metal. Phosphide is a non-metal. But what else can we call this single unit of this ionic compound? Is that a molecule? This is not a molecule, it is a formula unit. And in fact, I had written something down with my other class that I forgot to do with you guys. So perhaps we could take a moment and do that now. Is that, let's go back, where did I, never mind, we'll do it in a minute when I figure out a good place to do it. Okay, so remember that in element symbols, the first letter is always a capital, and the second letter is always lowercase. This is going to let you know when one element begins and the other ends. So if I wanted to look at KF, is KF, how many elements is it made of? 2, because I got 2 capital letters, right? How many elements is MGBR made of? 2, 1 capital letter, 2 capital letters. How many elements is NH4Cl made from? 3, 1, 2, 3. And NaNO3 is made from 3 elements, 1, 2, 3. In this unit, we are only going to concern ourselves with 2-element compounds. Next unit, unit 4, we'll do stuff with 3 elements, okay? But this unit's just going to be 2. Here's a little note. I have gone to special trouble to distinguish between the letter L and the letter I, okay? Your lowercase l no crossbars. And what do I mean by crossbars? I mean, if you have a capital I, you've got crossbars on the top and bottom. I have solely chosen fonts that have crossbars on the capital I. So if you see something that looks like this, what element or elements is that made of? That is made of chlorine. How many chlorines? 2. It's not carbon iodine. Yes? And I'll tell you, this comes up a lot. We get things like NaClO4, and people want that to be an I. Okay, this is in your next unit. It's not an I unless I put the crossbars on it. Yes? That would be an L, so ClO4. So not carbon iodine, but chlorine and oxygen. So watch out for that. It will become more obvious as you work with things more often. So here's Cl2. What kind of a particle is this? It's made of 2 chlorine atoms bonded together. It is a molecule. What kind of bonds do we have between the 2 chlorines? That is a covalent bond, which we'll be learning about a little bit later today and then on the long block. And in a covalent bond, the electrons are shared. So when you have nonmetal and nonmetal, so this is a nonmetal, and this is a nonmetal, the bond between them will be covalent, and those electrons will be shared, and you will form a molecule. Yes? Is this a compound? What would we need in order for something to be a compound. Sorry, what was that? Were you talking to me? You were mumbling. Okay, that's all right. You can mumble. No worries. It's all good. What would we have to have bonded together to make it a compound? We would need two or more different elements, whereas this one, the elements are the same, okay? Compounds need two or more different elements. So chlorine is not a compound. Okay. Ki. What kind of an element is K? What type of element? See, if you've got your periodic table kicking around, you can pull it out, or if you can look up at one of the periodic tables, it's on the far left. It is a metal, okay, so we've got a metal, and the iodine is a nonmetal. Therefore, what kind of a compound do we have? We have an ionic compound. What kind of a bond do we have between these two? That is an ionic bond. And what do we call this entire structure? A single unit of that ionic compound. That is called a formula unit. How do we know it's a compound? There's two or more different elements. Is it possible to have an ionic element? No, why not? Yeah, ionic by definition, you need a metal and a nonmetal. So by definition, those are going to be different elements. And if they're different elements, it is a compound, okay? Metals bonding to metals, they do that via a totally different process called metallic bonding that if you're interested in, I can give you some reading on, but we're not going to cover it in much depth this year, okay? All right. Now, let's take a look at this. This formula here, is that chlorine or is that carbon iodine? Carbon iodine because we've got the crossbars on the I. Yes? What kind of a element is carbon? Carbon is a nonmetal. Iodine is a nonmetal. So what kind of bond do we have here? That is a covalent bond. What's happening with the electrons? The electrons are shared. And what do we call this entire particle? We call that a molecule. So when the atoms are bonded together with ionic bonds, we call it a formula unit. When they're bonded together with covalent bonds, we call it a molecule, okay? And when they're bonded with ionic bonds, you won't really have any formula units. You will really have a bigger structure called a crystal lattice. Yes? Molecules don't form crystal lattices. Well, they do kind of, but we'll wait till grade like 11 to tell you that, okay? So just pretend I never said anything, okay? They can get together and pile one on top of the other, which is why you get sugar crystals, but anyway. Okay. We have some exercises, but I really, really, really want to make sure we get through the same amount of stuff as I did with my other blocks, so I will save these till the end. And we are going to watch a portion of a video on covalent bonding, and then I'm going to give you some work time, okay? So we are going to go, this is on page, is it 50? That sounds way too far. But maybe it is 50, no, it's 40. 40, page 40. Full disclosure, this video is a little weird. It's kind of strange. On the other hand, it is like literally the best simple explanation of covalent bonding with like, you know, pictures and stuff that I could find. And I've been looking for years. Every year I look and I'm like, surely something better is out now, because this is really strange. On the other hand, it kind of grows on you. You know, just have to put up with a little strangeness. Okay, so this is page, what page are we on? 40, 40. Page 40. Oh, and I need to plug in my sound. Plug in the sound. There we go. Make it larger.
Yeah. Oh.